All right, so good morning, everyone. This meetup is going to be in English. We have Hugo with us, who's going to deliver part 2 of his excellent session about the hash match operator. I assume that all of you or most of you have been in the previous meetup in part 1, or at least watched the session recording. I'm not going to go through the intro again because it's more or less the same. Just a few things I would like to say. I'll go through this. Okay, go to past summit, virtual groups, blah, blah, blah. Yeah, so this one, the previous meetup, just want to show you, if you go to the meetup page, previous one, part 1, you go down to the comments section. Then you have, first of all, you have the slide like this one, the slide of the community news. You have the session recording here, okay? And also, where is your link, Hugo? This one, right? Yeah, this one. And you have the link here to download all the session materials from Hugo's session. Okay, so everything is here. Let me maybe mute. I hear myself. Okay, so that's one thing. Let's talk about some upcoming events, and then we'll go to Hugo. So this week on Thursday, we have a session in our meetup by Ami Levin called 7 Deadly Sins of Database Design, a very good one. We have lots of registrations already. It's going to be interesting. So make sure you register for that session this Thursday at 7 p.m. On Friday, the next day, we have SQL Friday. SQL Friday runs every week on Friday noon. I have the honor to deliver a session this Friday called the most important performance factor in SQL Server. Want to be interesting as well. So this is on Friday, this one. And next week, September 1st, again, it's me. I'm going to deliver a session as part of our live webinars in Madeira about working with parameters in SQL Server. I did, again, this is also a two-part session. I did part 1 last month, and this is going to be part 2. Again, go to our website. You can find the previous session and access the session recording, session materials and everything so that you're ready for the part 2. And the next meetup after that, our meetup, is on September 6th, and it's going to be about the perfect multi-column index. Interesting title, I know. Ray Maor from Experta is going to deliver this session. And again, SQL Friday, we have another one of ours, Israeli, Eitan Blumin, is going to deliver a session about how to manage jobs in HADR environment. So it's going to be on SQL Friday on September 18th. So those are all the relevant events that we have upcoming in the next month. And that's all I wanted to say. If anybody has any questions, comments before Hugo begins, now is the time. Feel free to open your microphone or just write it in the chat. Anything, anyone? All right, Hugo.
I'll unmute myself and then I'll start sharing my screen. I always have to figure out.
Of course, please remember to ask questions during the session. Feel free to ask any questions.
Yes, of course, of course. I always forget how to share. Oh, yeah, I'm in the wrong menu again. So this should be it. You're seeing my screen now.
Yeah.
Okay. And I'll minimize you. Okay, welcome everyone. I hope you enjoyed last week's session on HashMatch the operator. So this week we're going to have a session on HashMatch the operator, part 2. First, let me introduce myself a bit. My name is Hugo Cornelis. I am a database consultant from the Netherlands. And I hope that most people are aware that I am building an execution plan reference website, basically providing all the documentation that I think Microsoft should have provided, but they didn't. So I'm trying to document everything that is there to know about execution plans. You can find it on sqlserverfast.com, where I also have my blog. And I have also started a project called Execution Plan Video Training, where I record videos about execution plans and try to pour all my knowledge into your heads. Today we're going to continue where we left off last week, which is the hardest part of this session. Last week I already told you hash match the operator is 500 level session. The first half is about 400 level. That was last week. And to compensate, we're going to do 600 level this week. So we're going to talk about memory usage. A full 75 minutes about everything related to how hash match uses memory and all the things that can go wrong. Last week we were living in the happy imaginary fairy tale world where hash match operators never spill. That world doesn't exist. So this week we're going to move into the real world where sometimes a hash match operator does spill. We're going to explore in detail what happens during a spill. We're going to talk about how a memory grant is computed, how an execution plan with multiple hash match operators reuses memory, and at the end I'm going to briefly mention hash teams. And by then I hope you're all completely phased out and dazzled and unable to do any productive work for the rest of the day. Your bosses will love me. So we're talking about memory, which means I have to start talking about something called the memory grant. The memory grant is the amount of memory attached to an execution plan that is requested at the start of a query. So when you submit a query, SQL Server looks in the execution plan to find the memory grant, which is the amount of memory needed to run the query, and requests that memory. Apologies. You can find the quick way to find the memory grant is just to hover the top left operator and look at the memory grant. Or you can look into the in more details in the properties window to find sub properties like required memory, requested memory, etc. Now here's how it works. In the execution plan there is this memory grant with those sub properties. When execution of a query is requested, the engine tries to reserve at least the amount of required memory. That's the minimum amount of memory the query needs to even be able to run. Without that, it cannot run. If that amount is not available, the query will wait. So if you have too much memory pressure on your server, sometimes you will have queries that appear to run slow. In reality, they ran fast, but they had to wait a few seconds before they got their memory available. If the memory is available, then it tries to reserve up to the requested memory, which is the amount of memory the optimizer thinks is needed to smoothly run the query. It is important to realize that once you request your memory and reserve it, it is and remains reserved for that query during the total duration. So if you have a memory grant of 500 megabytes and during execution you only use 20 megabytes, there is no point at all in the lifetime of the query where Microsoft will say, oh, you're not using that memory, I'm going to free it up again and reuse it for someone else. No, you reserved 500 megabytes, it's yours. Conversely, you reserve 500 megabytes, you have to make do with those 500 megabytes. There is, save for a few edge cases, normally there is no scenario where you get extra memory while the query is running. Which means that if you reserved insufficient memory, you have a problem. You reserved 500 megabytes. You're running, turns out you need more. When Microsoft built the product, they had to make a choice. What are we going to do in such a case? What are we going to do if we run out of memory while executing a query? One choice would have been, oh, just abort the query, give the user an error message and let them fix something and retry. That would have been an option they could have chosen, but Microsoft said, no, if we can find any way at all to give you your results, we do want to do that, even if it's slower. So that's where the concept of spilling was introduced. And we'll talk in a lot more detail about spilling later. Now, the amount of memory that is requested is based on the estimated number of rows. Last week, I talked extensively about the phases of the hash match operator, and you remember the first phase, the build phase, is where in most cases the entire build input is stored in memory. So determine how much memory to reserve, SQL Server estimates how large that build input will be. If we expect the build input to be 400 megabytes in size, then the memory grant would probably be somewhere around 500 megabytes. It's higher because there is a deliberate margin there. Microsoft always asks for more memory than it needs based on the strict estimates, because it knows the estimate is an estimate. It can be a few percent more. But if it's way more than a few percent more, then we run into problems. So while the execution plan is compiled by the optimizer determines, oh, I expect to have this amount of rows of that size, so this is the amount of memory I need for this operator. And then it adds those together for all other operators in the entire plan, with some caveats that we'll see at the end of the session. And that's the amount of memory it will request for the execution plan to run. And like I said, that's the amount of memory that SQL Server will wait for until it's available before execution starts. And that's the amount of memory that is then assigned, and the plan has to do all its work with that memory, even if the estimates are wrong. There is one relatively new improvement here. That's adaptive memory grant. That's a feature that was built first for batch mode only in SQL Server 2017. And then as of SQL Server 2019, it's supported in all modes. What adaptive memory grant does is, after a query is executed, it evaluates how the actual memory usage compared to the memory grant. And if the actual memory usage was way higher or way lower, then it will adapt the memory grant and increase or decrease it in the plan cache. So the next time the same execution plan runs again, you will get a higher or lower memory grant. Because this is stored in the plan cache, it lasts until the plan recompiles, and then the information is lost again. So what happens when we run out of memory? What happens if we request 500 megabytes, but we need a gigabyte? SQL Server cannot get extra memory. What it has to do, and this is the part that I expect everyone to already know, is spill to tempdb. And most of us, and until I started building this session, that's went for me as well, most of us, that's all we know. Out of memory, we spill to tempdb, it's slow. But I wanted to know more. I want to know exactly what happens during that process of spilling. It turns out, I did some Googling, I found that there is a process known as dynamic destaging. And dynamic destaging is made up of 4 different ways to handle a hash operator: the in-memory hash join, the hybrid hash join, the grace hash join, and the recursive hash join. Now, I want to point out these are called hash join, not because they apply only to the join operator, but because in literature, these are based on academic researchers. This is not all Microsoft's original work. And when academics do research into how to perform a hash operation, especially when it comes to memory shortage, they think about a hash join, which keeps an entire table in memory, and not about a hash aggregate, which only keeps the aggregates in memory, because a hash aggregate is far less likely to run out of memory. That doesn't mean it cannot happen. A hash match aggregate can run out of memory. It uses the same methods as mentioned here, but because all academic studies are related about hash joins, these are simply the terms you will find in academic studies. So if you want to search into the literature, you can type grace hash join or hybrid hash join, and you will find literature about these operations. But again,
Hugo?
Yeah.
Question. Are you talking now about what happens when spilling to tempdb in general, or just regarding the hash match operators?
Yes. I love it when people say ask an or question, and my answer is yes.
Yes.
So what I'm going to talk about is a lot of generic description about how the hash algorithm handles memory shortage. It's the way I describe it is focused on a hash join, but the same principles are applied to a hash match aggregate.
No, but I mean, what about a sort operator, for example, which
Sorry?
needs to split the tempdb? Is
Oh
it
no,
the same thing or is
no,
it different
I
process?
have never researched the sort operator yet.
Okay.
That's something I will probably do someday in the future, but I haven't done it yet.
Okay.
And this does not apply to the sort operator. Most of the stuff that I describe here simply cannot be applied to the sort operator.
Okay, thanks.
But I will talk about the hash. But I will talk about both, and this will be sometimes always ask if it's not clear whether something applies about the algorithm in general or the Microsoft implementation of the algorithm, because both are a bit mixed up in the next slides. So we have this dynamic destaging with its 4 components, but then we also have dynamic role reversal, we have bailout, and we have something called bit vector filtering. So all those elements combined are needed to handle the scenarios where SQL Server runs out of disk. So when we say it spills, that's 6 letters, we actually describe 7 different scenarios with just 6 letters. That's the only thing effective about spilling, by the way, because spilling is not effective. So let's start with the in-memory hash join. The in-memory hash join is actually the case I talked about last week. So when I talk about an in-memory hash join, that's the scenario where we do not run out of memory. The in-memory hash join is the algorithm that can only be used when the build input fits entirely in memory. And yeah, like I said, I described it in detail last week, so I'm not going to spend any more time on it. So that's where we start. Now I'm going to skip the hybrid hash join and move to the Grace hash join. I'll return to the hybrid later. The Grace hash join is an algorithm that is described as to be used when you know that you are going to run out of memory. So you start a hash match operator, and you know that you will need more memory than the memory grant you have been assigned. At that point, you can immediately start running the Grace hash join algorithm. And what happens here is that based on what you know about how large the input will be, or what you expect about how large the input will be, you divide the set of buckets into partitions. So last week we talked about this hash function, and we have all this input in the build input, and some columns are the input to a hash function, and that hash function has a known range. Let's say somewhere between 1 and 20,000. I'm not saying that's the actual range because I have no clue what the actual range is, but let's just use this as an example. So that means that our hash table will have 20,000 buckets. But now we're starting a hash match and we already know that we don't have enough memory. So what the Grace hash algorithm does is say, okay, I'm going to find a second hash function, one that uses the number of 1 to 20,000 as input, and that comes back with an output of 1 to 4. So that means that after finding the bucket, the result of the hash function, we can use that bucket number as the input to another hash function to find a partition number. And we have 4 partitions, 1, 2, 3, and 4. And again, this number 4 is just an example I use here to illustrate it. The actual number depends on how large we expect the input to be versus how much memory we have available. So for this example, I'm going to run with 4 partitions. So I'm going to recapture this again. We have a hash function that returns 20,000 possible bucket numbers, and each of those buckets is assigned to one of 4 possible partitions. Now we're going to create 2 files per partition. And I have files between parentheses here, because if you look at the generic description of the Grace hash join in academic literature, they will typically use files, and that's how it's described. But SQL Server uses tempdb, so it's not actually files that get allocated on your disk system. It's structures allocated within tempdb. So 2 files are created per partition, one for the build and one for the probe. So in this example, well, we had 4 partitions. the algorithm will create 8 files. And now it will read both inputs and store the rows in the appropriate files. So it starts with the build input. For each row from the build input, it will first compute the hash value, which is the bucket number between 1 and 20,000. It will, from that, compute the partition number, and then it will write that row to the appropriate build file. When it is done with the build input, it will do the same for the probe input. And at that point, the entire input, both inputs have been processed, and everything has been stored in 8 different files. And after that, the Grace hash join algorithm can start to process each of the partitions. So it starts with partition 1. It reads the entire build input from the file it created earlier and stores all the data it reads from there in the in-memory hash table, which now fits because we designed the partitions to be small enough that each partition will fit in memory. So after reading build input 1 and storing it in memory, it can start reading from probe input 1 and produce the output by simply pretending those are the inputs and the output of an in-memory hash join. So effectively, it's now doing an in-memory hash join between the files of partition 1. And then it clears memory, and then it does the same for partition 2. So that means that we have a full pass over both inputs to get everything in the files. And then we have full passes over each of the files to get the output we need.
Hugo, we have a question.
Yes.
While the query is running, can we see all of that information? Can we query DMVs or look in tempdb, for example, in syspartitions and see the objects, the internal structures, the number of rows in each?
No, you can see very little of this. If you want to know a bit more about how hard it is to look at structures for temporary files in tempdb, then I suggest that you sign up for Datamines Connect. That's October 14 or 16, I think. It's a virtual conference organized by my Belgian friends. And there I have a session where I talk about how I investigated the structure of a temporary table created by a table spool. I intend to one day find the time to do the same for the files created for the hash match, but I've never done that. There is no supported simple way to do it. It's incredibly hard.
Okay. And I have another question.
So you cannot see. The only thing you can see is in the execution plan and in the set statistics IO. You have some signs that spillings have happened, but that's all you see. And I'll show them. I'll point them out in the demos.
And another question. You mentioned here that you split the buckets into partitions. And
yes.
In each partition, you have the build and the probe. They have to match. How do you do that? Well, not you. How SQL Server does that? Without sorting the data first.
So we already have a hash. We already had a hash function on the original input.
Yeah.
That for each value that is used in the join, that's the key value for the hash input, comes up with a bucket number from 1 to 20,000. And as I explained last week, because the same hash function is applied to the build input and the probe input, if a row from the build input is in bucket 205, then every row from the probe input with the same key value will also be in bucket 205 because it's the same hash function.
Yeah, sure.
The same trick is done again for coming up with the partitions. So this bucket 205, the number 205 is input for another hash function, and this bucket 205 ends up in partition 1, which means that all build input from bucket 205 will be in the build file 1, and all the probe input for bucket 205 will be in the probe file 1.
So this means that before splitting into partitions, you first need to scan the entire build. And actually, the probe as well.
It's done while scanning the build.
Oh, okay, I see.
So the pure Grace hash join algorithm, exactly as described here, without any modifications. We'll come to the modification later, but as described here, can only be used if you know in advance that splitting the build input in 4 fractions will be enough to not run out of memory. Which is also not always the case, because you don't scan the entire input in advance.
Yeah, okay.
Is this sufficiently clear, sufficiently answered now?
Yes, thanks. Another question, is there a correlation between the number of partitions and the speed level that we see in the execution plan warning?
I guess there is, but I have no clue how it works. Sorry.
Okay.
The only thing I know about the spell level is the higher, the sadder you get. More questions?
No.
Good. I'll continue then. So the basic grace hash is what I just described, but there are some optimizations possible. Because the entire build input is processed first, and because the build input is what has to be in memory, the size of the probe files is not relevant. Apologies. There is an optimization. So let's say we have the same example where the 20,000 buckets are divided across 4 partitions, partitions 1, 2, 3, and 4. SQL Server processes the entire build input, and every row from the build input goes into one of the 4 build files, 1, 2, 3, and 4. When this is done, SQL Server knows exactly how large each of those files is. So if we have this 500 megabyte memory grant that I keep using as the example here the entire time, and if we figure out, hey, file 1 is 400 megabyte, file 2 is 150, file 3 is 450, and file 4 is 200, that means if you kept track of the numbers, that files 2 and 4 can be combined. Now, it will not change the files it has already created, but it will make a, let's call it a mental note. It will just be a variable somewhere to say partitions 2 and 4 are each small enough that they can be combined. And while it then, during the next stage, starts processing the probe file, it will only create 3 probe files. So now we have 4 build files, 1, 2, 3, and 4, a mental note that probe 2 and 4 can be combined, and we have 3 probe files for partition 1, for partition 3, and a probe file for the combined input of partitions 2 and 4. Then, after the build and the probe have been divided across those now 7 files, it will process build file 1 with probe file 1. Then it will load build file 2 into memory, immediately add build file 4 into the same memory, because we know it fits, and then process probe file 2 and 4 combined. And then it will do partition 3 as the last partition. So this is a small optimization that's possible because while building those, while creating those build files, it's insanely easy to keep track of how large they all are. And that was the grace hash join. But the problem is, I just described a happy scenario where build 2 and build 4 both were small enough that they could be combined. But what if, after creating those 4 first build files, we realize build file 3 is still 600 megabytes and we only had 500 megabytes of memory? So this can happen if you start a grace hash, but somehow you make a misestimation of how large each partition should be. So maybe you had just not enough partitions, or maybe there was a lot of skew in the data and it happens to be that a lot of the larger buckets all went to partition 3. And that caused partition 3 to overflow while partition 2 and 4 are still very small. Now we still have only 500 megabytes. We have a build input for partition 3 of 600 megabytes. That's not going to fit. So in this case, after build file 3 has already been created, SQL Server has to subdivide this, and I'll call this partitions 3.1, 3.2, and 3.3. In this case, it can use the statistics it gathered in the build phase. It has already processed every row that is in build file 3, so it has more information than it had at the start. So it can try to optimize the subpartitions, but then it will need to rescan build file 3, read every row it already had in build file 3 and now assign it to 3.1, 3.2 or 3.3. And it's called recursive for a reason. In theory, it could be possible that 3.2 then still is too large and we need to do it again. But let's not complicate our example too much. So now, combining everything we had so far, we start a grace hash join with 4 partitions. After the build, we decide partitions 2 and 4 can be combined, but partition 3 has to be split into 3.1, 3.2, and 3.3. Then the probe input is read, and every probe row is written to one of the output files. The file for partition 1, the file for partition 2 and 4 combined, the file for partition 3.1, for partition 3.2, or for partition 3.3. It's getting complex. But the benefit is, at the end of this, we have now all those build files and all those probe files, and we know we can process everything. But of course, this recursiveness means that we scan the same input multiple times and write it multiple times, so it's not effective, but at least we get to finish. Any questions so far?
Probably not.
Good. Then I'll continue with the one I skipped, the hybrid hash join. The hybrid hash join is the one that SQL Server tries to use when possible. And the hybrid hash join is sort of a combination of the in-memory hash join and the grace hash join. So with the hybrid hash join, SQL Server, or rather the hash match algorithm, because it's not just SQL Server that uses this algorithm, optimistically starts as an in-memory hash join. It's like every Hollywood movie you ever see where the main character says, what can possibly go wrong? Let's just store everything in memory. But like in every Hollywood movie where that quote is used, something goes wrong. Went out of memory, and that's the part where the in-memory hash join changes to a sort of grace hash join. So SQL Server happily is adding rows to its build input as an in-memory hash join until it realizes I'm running out of memory and there is still input, I need to do something. So at that point it says, okay, I'm going to partition and I'm going to create 4 partitions. I'm just going to keep using the same example over and over so that you can follow along. So at this point, those 20,000 buckets we had before are divided across 4 partitions. Now we already had a lot of data in memory, and that data will probably belong to all of the partitions. At this point, SQL Server also determines, okay, I'm going to keep one or sometimes even some of the partitions in memory, and the rest goes to disk. So here's an interesting difference. We have 500 megabytes of data in memory. SQL Server realizes I need 4 partitions. It's not going to create 8 files. For my example, it's going to create 6 files. It's going to create files for build 2, build 3, and 4, for probe 2, probe 3, and probe 4. Those files are empty at first. And then it will quickly, well, as quick as possible, go through the 500 megabytes of data already in memory, the entire hash table. Because every bucket in that hash table belongs to one partition. So for every bucket, it will determine, is this partition 1? Fine. I don't need to do anything because I'm going to keep partition 1 in memory. Is this partition 2, 3, or 4? Then I'm going to copy all the data from this partition into the build file and release the memory. Once this is done, everything that has been processed so far for the build inputs 2, 3, and 4 has been retroactively written to those files, and everything for partition 1 is in memory. And then it will process the rest of the build input, continue to build the files for 2, 3, and 4, and continue to build the hash table for partition 1. And yes, this is also a process that can recurse. Partition 1 can overflow again. Let's assume it doesn't. So at the end of this phase, we have the build input for partition 1 in memory already. It has never been on a work file. And the build inputs for 2, 3, and 4 are in their files. Now we can do the same trick with combinations, except that partition 1 doesn't qualify for combining anymore because it's already in memory. But for partitions 2 and 4, SQL Server will once more say, okay, I can combine them. And partition 3, once more, it's too large, so it will have to be split again. This is the same as with the grace hash. So at the end of that, we have the build phase completed. The hash table holds partition 1 in memory. We have build files for partitions 2, 3.1, 3.2, 3.3, and 4. And we have a mental note that 2 and 4 can be combined. Now the probe phase can start. During the probe phase, a row is read, its bucket is computed, and its partition is computed. If the partition is 2, 3.1, 3.2, 3.3, or 4, it goes to the appropriate probe file. And remember, 2 and 4 go to the same probe file. If it's 1, the row is processed immediately because partition 1 is already in memory. No need to write it to a file and then read it back later. It is processed immediately. And then when that is done, partition 1 has been completely handled, and all the data is in the files for partitions 2, 3, and 4 with splitting and combining as appropriate. And then the process continues as it would with a grace hash join for the rest of the partitions. Wheel. Questions? No questions.
I don't know what to ask. Where to start?
A proper question would be, is this all? And the answer is no, this is not all. We only started. Well, we actually went through everything that was listed under dynamic destaging. So what the Microsoft SQL Server implementation does is, depending on the estimates, what this Microsoft implementation does is hash match will always start as a hybrid. I see a very sloppy typo there. Let's imagine that I wrote hybrid. Starts as a hybrid hash join, which means it starts in memory, because hybrid starts in memory. It might degrade into a full grace hash join if there are too many files. And I just quoted this because I found it somewhere and I couldn't find any more information other than it degrades into a full grace hash join if there are too many files. So just take that as something I found on a Microsoft site. This is not a speculation site. This is part of Microsoft's documentation. It's just not very clear. And of course, if it needs to degrade into a recursive hash join, it will. So all those steps I just described, including the small optimization, are part of the dynamic destaging. But then there's more. There's also a dynamic role reversal. Dynamic role reversal is only possible when the files are already written. So in the case of the hybrid hash join I described before, where partition 1 remains in memory, in that case, partition 1 cannot use role reversal. But all the other files can. Imagine we're ready to start on partition 3.1. We know, because we kept statistics while building those files, that the build input for partition 3.1 is 300 megabytes. We also know, because we kept statistics during that file creation, that the probe file for 3.1 is only 50 megabytes, because it just happens to have a very skewed data distribution, and there were not that many rows in the probe input for that partition. At this point, dynamic role reversal says, let's, for just this partition, assume that you didn't write A join B, but that you wrote B join A. So now the probe input assumes the role of the build input assumes the role of the probe, because hash match is always faster and more efficient with a smaller build. In this case, what was the probe happens to be smaller, so they are reversed. And that's always possible. If you remember last week, for every hash match scenario, for every operation that uses a left somewhere, there is an equivalent that uses right. So when you have a left join A, left join B, SQL Server can always do B right join A instead. And this is done on a per partition basis. So you can even get this for some of the partitions, but not for all. And this can sometimes save a bit of time, which is good news because we already lost a lot of time with all that overhead with the files. So here we get a tiny bit back. it's not all good news. Bailout is where the really bad news starts. This is the process you really never, ever want to happen on your production servers, because your management will be very unhappy. So bailout is like the emergency exit, the help, I'm completely stuck and I still need to do something and everything else failed idea. So we have this recursive hash algorithm where we keep splitting the partitions, but at one point SQL Server gives up. I don't know exactly what point it is. In theory, you could have a partition of just a single bucket. And in theory, just that single bucket could already be larger than your available memory grant. Well, you can't divide a single bucket further, so that's the worst case where you have to stop recursing. I don't know if SQL Server continues until that worst case or gives up earlier, but there is always a scenario possible where there is so much data in a single bucket that no matter how often you recurse, no matter how often you split, you will never be able to fix that, to fit that bucket in your memory. At that point, there is no denying it. You simply cannot process this with a hash match. It's simply not possible. If a single bucket uses 600 megabytes and you have 500 megabytes of memory, you're out of luck. And again, Microsoft could have chosen to, in this case, just abort the query. But they didn't. They said, we still want you to have your results. So at this point, it will switch to either a nested loops algorithm or a merge algorithm. One of the two other joins. Based on what it knows about the data, it will make a runtime choice between which of the two. And I'm here to tell you that whatever it chooses, you will be unhappy. So to set the stage, we have already read all the input in those build files and in those probe files. We have repeatedly scanned those build files as we recursed into smaller and smaller build files. So we have already processed the build input multiple times. All written to tempdb. And yes, tempdb uses the buffer pool, but we ran out of memory. There is a high likelihood that we had a lot of physical I/O going on here. We are already pretty unhappy. And now we end up with at least one partition where both the build and the probe are larger than the memory grant, more than 500 megabytes. We are already pretty unhappy. And now the bailout starts. And option 1 is a nested loops. Nested loops means we read one row from the build and we find the matches in the probe. The probe is a file we just wrote to tempdb. It's not indexed. So how are we going to find all matches in the probe? By scanning the entire probe, more than 500 megabytes. And then we do the same for the second row from the build, and then for the third row from the build. And that's not going to be nice. That's going to be terrible. So perhaps a merge join algorithm is better. I mean, the merge join algorithm scans both inputs exactly once and flows them together. Yeah, but they have to be sorted. So just sort the data. Yeah, but we have two files of 600 megabytes each. They need to be sorted. And we had 500 megabytes of memory. What happens when you try to sort stuff and it doesn't fit in memory? Your sort algorithm will spill. So your sort algorithm will be incredibly slow and you have to sort two files. So whichever option SQL Server chooses at runtime, it will be terrible.
Do we get an indication of bailout in the execution plan, or does it still look like a standard hash match operator?
I think it looks like a standard hash match operator. I don't know. Perhaps I have never ran into bailout. That is possible. I think it's not something I have on the top of my head, but I think if you look into extended events, you might find something there. But I'm not 100% sure. Now, the good news is that a bailout doesn't happen for the entire hash match. It happens on a per partition basis. So if it is indeed partition 3.2 where this happens, then it's only partition 3.2 where this happens. All other partitions will still use their normal algorithms. Let's return to some slightly better news. There's also a process called bit vector filtering. What bit vector filtering does is, while it creates the build input, it will, apologies. While it creates the build input, it will keep a small bitmap with 1 bit for every bucket. So in that example, you've been using the entire time 20,000 buckets. That's a bitmap with 20,000 bits. That's 2,500 bytes. 2.5K, nothing. In that bitmap, it will track whether or not at least 1 row is in that bucket. So during the build phase, and the build phase can be either an in-memory build phase where it's just building a hash table in memory, or it can be a hybrid or grace build phase where it's stuffing data into files. But regardless, every row read from the build input gets first hashed to a partition number, to a bucket number. So then it can set the bit for that bucket number to track in the bitmap that there is at least 1 row in that bucket. What's the benefit here? This is just a few instructions, just a few kbytes extra memory usage, so there's very little overhead. What's the benefit? The benefit is that when it starts reading from the probe input, every row from the probe input also gets hashed to find the bucket number. And instead of searching the bucket or writing it to a probe file, it can now immediately dive into the bitmap table and say, hey, this bucket is empty. So I don't need to do anything. I already know that this is a non-match, and I can handle it as a non-match, which means for an inner join, I can ignore it. For a write outer join, I can write it to the output, etc. Only when the bit is set, then the hash table will be searched if it is an in-memory partition, or, and this is where the real savings come in, or the row will be written to a probe file and read back later in memory for further processing if it is a spilled partition. And you can imagine if this happens to a lot of rows, that you save a lot of overhead because you're not writing those rows to a file and then reading them back later. So this is where, especially in the case of a spill, bit vector filtering really saves some performance. Let's jump into a demo and see this in action. Let's first check my time. Okay, I'm still good for time. Let's jump into the demo. I'm going to use the same sample database I used last week. Now I have a query here. And this query looks very similar to the same queries we used before. It's the same structure as the queries I used last week. I'm very unoriginal that way. But what I did now is the top is a variable. Here are the real values. But I tell the optimizer, pretend it's going to be these values. Now you will see the build input will be 500 rows in reality. And I tell SQL Server to optimize for 1,000 rows. So it will overestimate the size that is needed for the hash table, and I expect that this will not spill. And indeed, it doesn't spill. So let's review a few things. At the select operator, I can here see the memory grant. So based on what I told SQL Server to expect 1,000 rows, this is not based on the 500 of reality, but I told SQL Server expect 1,000 rows. Based on that, it estimated a memory grant of 2,528 kilobytes for the entire execution plan, which in this case is basically for the hash match operator, because the rest of the operators have no weird memory usage. But I can also look at the properties here. And here you will see the same memory grant, but I already opened the memory grant info, and here you will see a lot more information. So this is the minimum requirement. It could have run in just 1 megabyte. There is serial desired and required memory. So in case the plan runs serial or parallel, these can be different numbers. This is the requested memory, but you also see how much memory was actually used. So here we already see that because I forced SQL Server to optimize for 1,000 rows and then gave it only 500 rows, over half of the memory was unused. That's not terrible, but if it happened on a very busy system, with lots of people using memory, you also don't want to overuse memory, because then people will have to wait for your memory. Now I'm going to do the same thing, but I changed this estimate to 100. So now I'm still going to build a 500 rows, but I tell SQL Server optimize for only 100 rows. And in this execution plan, you will see some indications of spilling. So you will see this warning symbol on the hash match. And if you see that warning symbol, you can always hover your mouse and you will see a warning text. These warning symbols and texts were introduced in SQL Server 2012. So if you're running a really old SQL Server version, you will not get this information in the execution plan. You will still get extended events information, but not in the execution plan. I hope nobody here is still supporting SQL Server 2008 or older. So here you will see more information. The operator used tempdb to spill data. It was level 1. It was one spilled thread. We wrote 64 pages to. We read 64 pages from. And we also have some information about the granted memory and the used memory. So there's quite a lot of information here. And that has also been improved over the time. In SQL Server 2012 and 14, the warning message was a lot shorter. This is SQL Server 2019. We get a lot of information. We also have some information in the statistics IO. You will see that there is a work file here. And it's called a work file because it's the files that SQL Server creates for the spilling. A work table is a table structure in tempdb. A work file is a file structure in tempdb. And so far I've only seen work files with hash match. And here we see the same 64 logical reads that were also in the execution plan. 64 pages read. There were also 64 pages written, but yeah, there's only reads here, not writes. So you don't even see that in the statistics IO. You do see that there was a spill. If we rerun the first query, which didn't spill, you don't see a triangle here, a warning, but you also see here that the work file is still allocated, but the number of logical reads is 0. It is not used. So every time you have a hash match in your execution plan, you will see a work file in the statistics IO, but it will be 0 if it doesn't spill. And it will be non-zero if there is a spill. Let's take this a bit more extreme. I'm going to build select 2,000 rows from the build input and 2,000 rows from the probe input. I'm going to tell SQL Server to optimize for 100. So there will be some bit more extreme spilling here. We're going to look at a lot of interesting stuff here. First, I want to show you that I used a full outer join. And remember, last week in the full outer join, you will remember that the data is returned in the order of the probe, with non-matching right rows at the end, and then the non-matching left rows are returned at the end in whatever order they were in the hash table. That order appears to be the same if you look at the screen now, but if I scroll down, you will see that later the order is completely different. Let's look into in a bit more detail. Now what you see at the start is that there is an insane amount of right retained rows. Almost every row that has a letter C or E is here. Well, we know from how I created the build inputs that those C and E rows don't match, but they don't all go into the same partition. This is bit vector filtering. The probe input is processed after the entire build input has been built and divided across several tables because we spilled in this case. So I didn't show that, but here you see that it did indeed spill. Come on, pop up, do what I want. Yes, there you are. In this case, the spill was 240 pages. So what happened during the build, it started in memory, then became a grace hash, writing a lot of data to files in tempdb and keeping some data in memory. After that was done, it starts processing the probe, and that's when it first can start to return rows. So for the first, but with the first partition in memory and other partitions on disk, it reads the probe input, and when it encounters something that happens to be in partition 1, it can return that. But if it encounters something that's in a different partition, and I don't know that this is a different partition, it's just an assumption, it uses the bit vector to see, oh, but this goes to an empty bucket. So I don't need to write this to a probe file and then read it later and then determine it's not a match. The bucket is empty. I have that bitmap. I don't know what would be in the bucket if it's not empty, but I do know that this one is empty. So that's why almost all the non-matching rows from the probe input are returned in their expected order when the first partition is being processed. And that continues for a while. So this is all processing of the first partition until we reach the end of the selected data, which is about here. And now we get, well, here, this is the last one. And now we get a change. Now we suddenly get a lot of data where the left row is, the left table is returned and it doesn't match anything. This is also a considerable chunk until about here. Now what happens here, and this is a part that I don't fully understand, but I think what happens is that perhaps the partitions were not completely matched. I think, again, it's not 100% sure, but I think that at this point, SQL Server realized, hey, I have a build partition that has an empty probe file. So I'm just going to process that entire partition as unmatched. This is not entirely sure, but I think that's the explanation. After that comes a part that I can explain better. So what we see here is again data with matches and non-matches interspersed, but now in the order ascending of the left table. That is not what we expect from a full join, and yet we get that. But here's the reason why. Because I used, and I need to scroll a bit here, because I used the same size for the probe and the build input, they would be the same size. But remember all those non-matching probe rows that, due to the bit vector, were already kicked out in advance? Here's the thing. After kicking out those rows, the probe file is now smaller than the build file. So this is where we see dynamic role reversal. It's actually doing a join, a full auto join between the probe and the build, and not between the build and the probe. And that's why, because the build is now functioning as if it's the probe, the data is ordered in build order until we hit the end of the partition, and then we start on a new partition which does the same. And that process repeats until the end of the output. So by just looking at the output and understanding all the mechanics, we see all those things going on. We see all those things happening, and we get indications of how this affects the order. Are there any questions at this point?
Yes, one question and one comment.
Good.
Question first. In many cases, when I look at the execution plan and there's a hash match join, I see a bitmap operator on the build input, and then on the probe input, you see a probe predicate.
Yes.
Is this the bit vector filtering, or is it something else?
This is something else.
Okay, so can you explain the difference?
I do not have time for a long explanation, but I can Come on. I need my taskbar somewhere. Let's just jump out here. Want to know more? I can recommend that you go to my website, go to the operator list, and go to the bitmap page. You will find some description of what the bitmap does with there's also some description of that probe on the index scan page.
Okay.
Where this is a rather long page, but it's mentioned somewhere. I don't know exactly where, but I know it's there.
Okay, thanks.
It's not in scope for this session, so that's what I'm going to where I'm going to leave it. And if the person asking that question still has questions after reviewing those pages, my mail is open.
Okay, thanks. And Michael says that there is a hash warning event, both in extend events and in SQL trace, where you have the subclass property. If it's 0, it means recursion. If it's 1, it means bailout.
Wow, thank you.
Yeah.
Good addition, thanks. Okay. We talked about how terrible things happen when your memory grant is insufficient. So by now, I'm sure nobody wants the memory grant to be insufficient. So how is the memory grant computed? Well, there's a lot of stuff that influences it. Obviously, the estimated size of the build input. The build input is what is supposed to be stored in memory. So obviously, the amount of rows in the build input and their estimated size determines mostly what the memory grant should be. Here it is important to remember that if you have varchar columns, they are assumed to be half full. Same goes for char columns, by the way, because they are internally stored in a more optimized format. So to everyone who says, hey, I know my data is never going to be more than 20 signs, but I'm going to do varchar 8000 anyway, because then I will never have runtime errors. Well, you just told SQL Server to reserve 4000 bytes per row for each of the rows in the hash table. And you're going to use a lot of memory and probably going to spill. So maybe you should rethink those data types a bit. Surprisingly, at least for me, it was very surprising, the estimated size of the probe input is also, to some extent, taken into account for the memory grant computation. What is not taken into account is which columns are used in the hash function, what the hash keys are, or what logical operation is used. Whether you do an inner join or a full outer join or a left anti-semi join, they all use the same memory grant for the same input. Aggregate and flow distinct are of course the exceptions here, because they store the aggregated data. So of course they have a different memory grant. So I'm going to skip most of this demo, but show a few things if I can find the right screen. Yes, this is it. So what I used again are variations of the same query. Make sure we're in the right database. What I did here is all actual numbers are small, but the optimized for numbers are larger. So why did I do this? Because the easiest way to find the memory grant is in an execution plan plus runtime statistics, also known as actual execution plan. So I want to run the queries and not just request the execution plan only, because then it's more work for me, more mouse clicks, and I'm lazy to find the memory grant. So I keep the actual number at 100, but I vary the amount I ask SQL Server to optimize for. So I have several queries, one with a hash key of key 1 and key 2 combined. Here's the same query with the same numbers, but joining on only key 1, and here on key 1, key 2, and filler, which is a varchar for 8000 column or something like that. So if a hash key size has influence on the size of the hash table, it would affect the memory grant. And yet, if I execute these 3 queries, I can just look at the first execution plan and say, oh, the memory grant is almost 60,000K. The second one hey, same number. Third one, also the same number. Now I kept doing that. Here is a block where I varied the join condition. Here I varied the number of rows. 1 million. No, sorry, I varied the join type. This is an inner join and this is a full outer join. Here I did vary the, I need to read commands before. Yeah, here I did affect the join type because here we need to store key 1 and key 2. Here we need to store key 1 only, and here we need to store key 1, key 2, and filler. I'll just run this one as an example. To see that in such a case, the first has a memory grant of 5600K, the second is slightly lower, and the third, where we had to store that large string column, we suddenly need almost 30,000K. So this is something that does affect it. There's more examples. The estimated row count of the build. But I also looked at the estimated row count of the probe, and to my surprise, I found that if you have 10,000 rows in your build and 100 rows in your probe, or 10,000 in your build and 1,000,000 rows in your probe, you would expect the memory grant to be the same because you're just storing the build input. The probe input shouldn't affect it. And yet, to my surprise, the memory grant went from 1584 to 3136, and then finally up to 8860. I ran all those experiments varying different things, and when I found an influence, I ran way more experiments with way more values, and I didn't even include all the demos I ran in the file because it's just changing numbers. But what I did do was collect all the relevant information in an Excel spreadsheet. So the first example is where I used an integer NHR1. The probe size was set at 1, and the build size, I used all these different values. So I've tried for all those values, and I've written down what the grant was, and I've plotted that. And you see in the first plot that only uses the start of the table, that there are 3 straight lines and then drops. And in the second graph that uses plots the entire data, you see the same here, but of course harder to see. And the third straight line continues all the way up. If there is a fourth drop, I haven't found it. So apparently for this case, there is a linear correlation between the build size and the memory grant, but there are 2 drop-off points where the formula changes. You see that the angle of the line changes slightly, and you see that the base changes. So I have found the formula, and the results of the formula in this column, you can see how close they are. This is the formula that most accurately describes, for this specific case, how it works. I've done the same by adding a character 1000 column, and I saw the same structure with different values because the character 1000 means that the memory grant is many more bytes per row. So the amount of rows has a much larger influence here, obviously. Here I kept the build size at 1, which is insanely small for a build size, and I changed the size of the probe. And here we also saw a correlation, but the correlation was far less. Yes, it goes up, but it goes up from 1056 to 15,060. And as you see, especially in the right side graph, it's what's the word again? Normally logarithmic, that's the word I was looking for. That's a logarithmic correlation. So the memory grant logarithmically increases with the probe size. I still don't understand why Microsoft built it this way, but this is clear what happened. If you look at the left side table, you see a straight line here, which is because there is simply a lower limit. SQL Server will never go below 1056. Never. Here I do the same but with a larger table, and we see the same logarithmical increase, but now we also see a drop-off point in this computation. And then I have 2 more where I added, where I did the same variation with the build probe size, but with a larger starting build size. So now I have the build size at 10,000, and again I'm varying the probe size. Then you see a linear increase first, then a horizontal plateau, And after the horizontal plateau, you will see the logarithmical increase. And again, with a larger build input, because there's a char 1000, the same structure. So this is a lot of data and still far from sufficient to completely reverse engineer the algorithm. I still don't know exactly how it works, but I have seen some interesting correlations. So what I have seen is that if the probe is not a bit, but a lot larger than the build input, then, no, let's start at the top. I forgot the top line. First of all, basically what you would expect, the build input, the size of the build input has a very linear effect on the memory grant. If the estimated size of the build input goes up by a factor 10, the memory grant will go up by a factor 10. That's the part I expected. Everything else was for me a surprise when I started investigating this. So when the probe input is not a bit larger than the build input, but a lot larger, then it will assign extra memory to the memory grant using a logarithmically decreasing formula. I have found 2 points at 2 megabytes and 6 megabytes where the build formula changes. The base gets lower and the factor gets lower. I've also found that if the probe input is not a bit smaller than the build input, but a lot smaller than the build input, then there is a linear reduction. Not logarithmic, but linear. And then the final rules, it's always a multiple of 8K. It's never less than 1056K. And of course, if you have a limited memory on your machine, or you have limited settings, for instance, by using a resource governor, then your memory grant will never be more than the maximum. All these factors are taken into account when computing the memory grant. Now, how useful is this? Not very, because there's one thing that's really missing from this list. There is no way for us users to influence this. There is no way for us users to add a hint to tell SQL Server, hey, for this query, I know that these are your estimates. I know that they're wrong. I'm not trying to influence them because the execution plan is still okay. But please change your memory grant for me. And I don't think that will happen because now that memory grant feedback is there, that basically does that by just learning from its past mistakes. But before memory grant feedback was there, I really sometimes missed the option to tell the SQL Server, I know better than you what the memory grant should be here. Okay, so far all execution plans I showed were simple, just a single hash match, nothing more. Real execution plans are not simple. Real execution plans tend to use multiple hash match operators or sort operators that also use a lot of memory. So what I explain here applies to sort just as well, or actually to the combination of sorts and hashes. In this execution plan there are 4 hash match operators. I've numbered them so I can easily explain how this works. Now what SQL Server could in theory do is say, okay, hash match 1 needs 10 megabytes, hash match 2 needs 100, hash match 3 needs 90, and hash match 4 needs 150. Let's add it all together. 10 plus 90 plus 100 plus 150 is 450. SQL Server could have done that, but it doesn't. Because SQL Server knows how hash match operators run. It knows that hash match operators sometimes block. So let's analyze the various phases of this execution plan. When this execution plan starts running, all the operators starting at the left will call each other, and the hash match will call data, and this data will be returned. And this hash match will simply keep calling the upper branch because it's building its hash table. So the first phase is just hash match operator 3 calling its build input and building its hash table. At this point, operators have been initialized, but the only operator that is using memory is hash match 3, as it's building its inputs. So it's slowly increasing its memory footprint until the hash table is done, and then hash match 3 will start its probe phase. So it will call rows from the lower input, process them, and return them to hash match 2, which will then happily put them in its hash table. At this point, hash match 3 still needs the memory. The hash table it has created is relevant. It needs to remain in memory, but hash match 2 is starting to use memory as well because it's starting to build its hash table. So near the end of this phase, we have in memory the nearly or fully completed hash table for hash match 2, and we still have the hash table of hash match 3 in memory as well. Then hash match 3 completes, and the next phase starts. At this point, hash match 4 is requested for rows, and it will just do this. It will get a row, store it, get a row, store it. So you may wonder why I have included hash match 2 in the yellow marking. That's because the yellow marking doesn't indicate which operators are doing work. It's indicating which operators need memory. Hash match 3 has completed its work. The data it had in its hash table is never used anymore. So hash match 3 can at this point release that memory back to the execution plan, which means that hash match 4 can use the same memory that hash match 3 used previously. So our total memory grant is not the total of all hash match operators that are the same active at the same time, but it's the maximum of all hash match operators active during a phase. And the last phase is when hash match 4 starts its probe input. Data is still in memory for hash match 4, used to probe the input. Hash match 2 is also probing the row, so it also needs its hash table. And the hash match aggregate is now starting to fill its hash table. So at this point, there are 3 hash tables in memory. And then at the end, the final phase of hash match 1, it's only that operator using memory. How can you see this in the execution plan? By looking at the memory fractions in and the memory fractions out properties. So I've created a query that it looks complex, it looks weird. I do all kinds of crazy, insane, weird things in here. It's not relevant what I'm doing. What is relevant is, sorry, I wanted to execute this, just this, and then get an execution plan for this. I execute this. And then I don't know what went wrong, but I must have overlooked an error message. Get the execution plan here, and this execution plan matches the execution plan I showed in the slide. So this is exactly what we just saw. Wait. Here, this execution plan. Like I said, there is this property called memory fractions, and I'll click it and I'll then zoom in. Wait, I'll just shift this to the right a bit. So you see memory fractions input is 1. Remember when I showed the animation when this hash match operator, which was number 3 in the slide, is building its input, is processing its build, that's the memory fractions input. It's the only one using memory. So when the input phase of this operator was active, it could in theory use 100% of the memory. But during its output phase, it had to share memory with the build input of the one to its left. And apparently, based on how large or small the data was expected to be, SQL Server says you get 5.6% of the memory, and the remaining 94.3% are for the build phase of this operator. And there you see the remaining 94.3%. When this operator is outputting rows, it is at first sharing memory with only this hash match, and later sharing memory with this hash match and this one. The worst case scenario, it can use 94.6%. When this hash match is building its input, it's sharing data with only this hash match. And now the numbers don't add up, and that's because when this operator is building, it shares memory with this one and this one, but it can't add up to 100% because when this one is processing data, it's sharing with this one and this one, and this one. And that's why there is a phase where the numbers don't completely add up. But all those numbers give you some insight in how the memory can be distributed. What actually happens is that SQL Server determines those numbers first, and then based on the total memory grant of each operator and those memory fractions determines the total memory grant it needs for to run the entire execution plan. Questions?
Nope.
No questions? Good.
No questions.
I already did the demo. I just forgot the animation. So much effort in that animation. Copy paste in every presentation I do. Let's move to hash teams. I'm actually a bit over time already, but I'm going to continue just for tradition to always run over a bit. So I'm going to briefly touch on hash teams. What a hash teams does, and there is very little documentation on this, and there's also very little visibility in the execution plan. But hash teams is a special case where SQL Server realizes, hey, I have multiple hash match operators, and they all use the same hash key. That is crucial for hash teams to be active. If hash match operators have different hash keys, hash teams does nothing. But when multiple hash matches have the same hash key, then a team manager is assigned, and that team manager coordinates all those individual hash match operators. So then they all use the same hash function. The team manager decides how the memory is determined. The team manager determines the bucket to partition mapping if there is a spill. And the team manager coordinates all the spilling and restoring. And this gives a slight performance benefit over having each hash match operator do its own work without coordination. Because in this case, all the spills are at the same time, and that simply is slightly more effective. So let's run my last demo, then I'm going to wrap it up. This is the same query I used before in the previous demo. I just select the two queries I have here. I'll just select this query and show the execution plan. It's the same execution plan again. But it's not really the same. You don't see it here, but here all the keys are the same. In the previous demo I had different keys everywhere, and now they are all the same. I skipped that, but you can look at the memory grant and you will see that the memory grant is slightly lower in this case because SQL Server knows I'm going to use hash teams. That's more effective. But the query I want to show is the one where I use a really large number. So this query will run for a time, and I'm going to kick it off first. And while it's running, I will tell you that the first query can use hash keys, can use hash teams. Because here we have a join on key 1. Here we have a join on key 1. Here we have a join on key 1, and we have a group by key 1. So all the hash matches use key 1 here. And I optimize for 1,000, and in reality is 500,000. So yes, this is going to spill dramatically. Here is the same query structure, but now there is a join on 2 plus key 1. And there is a join on 1 minus key 1. And there is a join on key 1 times 2. And a group by key 1. And I know that it's still effectively the same, but SQL Server doesn't realize it anymore. It looks different, so SQL Server will not assign a Teams manager here. And if the query is finished, which should be any time now, it's busy returning the last rows to the client right now, finished. Now you will see that the first query, which used hash teams, had a runtime of 28.3 seconds, CPU time 25.3 seconds. And yes, we spilled 288 scans and 92,800 logical reads. So we really had severe spilling, but at least we had hash teams. The second query, which does not have hash teams, had an execution time of 34.7 seconds. Had a CPU time of 27.6 and had almost 50,000 more logical reads than with the hash teams. So both queries spill severely, but the one with hash teams at least gave me somewhat less terrible performance. And that's the benefit of hash teams.
Nice.
And that's it. Are there any last remaining questions?
Well, I have, I think, a basic question. You explained
After
very
all
well.
this, you have a basic question. Okay.
I think so. Yeah. But I'm sure you can help me with that.
What is an execution plan?
In the first session, you explained very well the structure of the memory, the hash table in memory.
Yes.
Right, which is basically consecutive memory addresses, which are the hash values, right? And within each bucket in memory, you have, I think it was 7 slots. Each one has a pointer to the data itself, and the pointer is 8 byte, 16 byte. I don't recall. But anyway, you don't store the actual values, the raw values inside the hash table. And now you mentioned that there is a big difference in memory grants when you use, for example, varchar 8000. It says you said SQL Server assumes you use half 4,000 bytes and it affects memory grant. But if it's not stored anywhere in the memory in a hash table, how does it affect memory grant?
That's a good question. So the memory.
It's not the basic question.
It's not really basic. It's rather advanced. So the hash table does indeed only store a pointer to the data, but the data is still somewhere in memory, and that memory has to be reserved while that hash table is active. Otherwise, if that memory were freed up and someone would start writing something else in that memory and my hash table still points to that, I will get very weird results.
Yeah.
And I don't get very weird results when I run a hash match, so that alone proves that the memory gets protected. So SQL Server doesn't physically move all those bytes of the varchar into the hash table. It simply puts a pointer in the hash table, and it uses whatever logic the operating system have to say, this memory is mine. You can't touch it. It protects the memory where the data is stored.
And this is part of the memory workspace, memory grant.
Yes.
Not just the hash table itself.
Because a normal operator, if you look at a normal, all operators are normal. If you look at a different operator, for instance, a nested loops also uses memory. A nested loops also grabs a row.
Yeah.
But it's just a single row. It processes that row, it returns it, and then it's done. So there's no memory grant for that, but it still uses some memory, which is also included in the memory grant for the total query. It's just so small that it really doesn't measure much. But the memory usage doesn't mean that the memory is all moved to a separate area of the memory that says this is the hash table. It says this is the amount of memory I can claim. And wherever in memory it is, I don't care, as long as you don't exceed it.
Yeah.
Because you need to share with others, and this is the amount of memory you can claim. Does that answer your question?
Yeah, sure.
Good.
Thanks.
You're welcome.
Michael has a question. So actually, the only option to try and avoid spills in a particular query is playing with top and optimize for.
No, playing with top and optimize for is especially a very effective way to force spills for a demo session such as I did today.
So what options do we have to avoid spills?
I would always start with just writing the query in the logical way. Always start there, because you also need to maintain it and your successor needs to maintain it. And I always like to think that my successor might be a crazy ex-killer who has my address. So I like to give him code that doesn't incentivize him.
That's a good point.
If the performance is bad, and in the case of a hash match, if the logically written query spills, investigate why. Most of the time, a spill is caused by a bad row count estimate. So you look at the build input, major contributing factor. You look at what is the estimated number of rows, and how can I fix that? In the case of the demo queries I used, fixing it is very easy. Don't put nonsense in your queries, because I deliberately put nonsense in there. I wrote a query where I said, I know I'm going to feed you 1,000,000 rows, but please pretend it's going to be 100 and give me the optimal execution plan. If you do that, there's a very easy way to fix it. Stop telling it to optimize for 100 plants if you intend to feed it 1,000,000 rows. Real queries are harder. Real queries typically don't use that kind of nonsense. Those that do are easy wins because you can do your work and charge your hourly rate without much work, but most of the time it's just more complex. But the basic idea is look at your build input. So let's just look at the query that's built. Let's do the smaller one because this one is going to run for half a minute more. So if you have an excuse me, well, they don't spill, but let's assume that this hash match is spilled. So let's assume that here we have this triangle symbol. What I then do is look here at this one and say, what is the actual number of rows? And what is the estimated number of rows? If there was a spill here, 99 out of 100 cases, you will see that the estimate is too low. And then you just start troubleshooting, why is the estimate too low? What is wrong there? Are statistics out of date? Are the statistics created with a small sample size? Do I have an ascending key problem? Is the query so complex that SQL Server simply cannot come up with a good estimate anymore? Did I use constructions that defy good estimation, etc., etc.? And then you start to fix that. In many cases,
it's a matter of parameter sniffing.
Can be. Doesn't need to be, but it can be. But there can be multiple reasons. Parameter sniffing can be one. Well, let's rephrase that. Bad parameter sniffing can be a reason. Parameter sniffing isn't always bad. It has a bad name, but it's not correct. Parameter sniffing is actually a very useful scenario, but sometimes it backfires.
Enough that you have joined on 2 keys. For 2 keys, you can't have statistics. You have only density vectors, and it's pretty inaccurate. So you have a lot of cases when you can't actually properly estimate the number of rows.
The hash, the estimation for the input of the hash match is not affected by what you join on. So if I look at this query, let's move this up and then put this back. This join correlates to this one. What I have here is irrelevant for this join. What is relevant is how many rows are going to be stored in the build input. So this is where you need to focus if this operator overflows its hash table. Then you need to look at, okay, what is wrong with build? And in this case, there is nothing wrong because I use a top 1000 and it doesn't overflow because there is nothing wrong.
Sorry, not
if you have a problem here,
if you have a
problem here, then you're going to look at this estimate, which can be a lot harder because this estimate is the result of a join. And estimation after a join is very hard. And it's not related to statistics. Well, somewhat. That's another 90-minute session I have, but let's not do that now.
Okay. Any other questions? Anyone? No, I think we're done.
Okay, thanks everyone for your attention. I really hope that you enjoyed it. I know that a lot of the stuff I covered is very deep, very internal, and not directly usable in your day-to-day practice. I still hope that you found it interesting and that you think it's interesting to know a bit more than just, oh, it spills, we're unhappy. Now you know a bit more about everything that's going on under the cover with a hash match with spills. I hope it helps you. I hope you liked it. Yeah, Guy, thanks for inviting me. Thanks for giving me the insane amount of time to do a double session for your group. Thanks for the invitation.
Thank you very much. It was excellent. I enjoyed it very much. And remember, everyone, we'll have this the recording of this session in the meetup page, I guess in a few hours or so. And don't forget to register and attend the next meetup this Thursday with Ami Levin. So see you. Thanks, Hugo. Bye.
Bye-bye. Thanks.